Good afternoon. Can we have it a little louder, please? Good afternoon. Okay. So, B-Space went down at 2:46 on Saturday morning. So you haven't been kicked out or anything. We repaired it all weekend long, and it's up again. Most of it is up again. So somebody who had access to B-Space, I don't know why, decided that he or she doesn't want to be on B-Space, and he or she had instructor access, and deleted his participation, and with this deleted the whole site, okay? Was not a hacker, but anyhow. So the last time, we have talked about the atom and the nucleus, and we found out that the mass of an atom is mostly in the nucleus. It's the mass of the protons and the neutrons. The mass of the electrons that are far away from the nucleus, we found out is very little. It's about one electron is about 1/2000th of the mass of a neutron or a proton. But you cannot neglect it when you make mass calculations. And we also found out that the nucleus itself is very small compared to the extent of the atom. There was about 10 to minus 10 nanometers was the size of an atom, and the size of the nucleus itself. Anybody remembers what was it in meters? Nobody? 10 to minus 15 meters. So that's 5 orders of magnitudes. If I have a quarter here or a dime, which would be the nucleus, the electrons would be out at the Berkeley BART station. Okay? There's a whole lot of nothing in between the nucleus and the electrons, and we actually don't know where they are. So then we talked about the possibility of determining masses. And I explained to you a rudimentary mass spectrometer. Of course, these instruments are much more sophisticated than I explained it to you, but you use a mass spectrometer, you ionize your compound, then you accelerate it in an electric field, and then you put it through a magnet, which charged particles will deflect in the magnet when they charge the moving particles, and the amount of the deflection will give you exactly a relationship to its mass. Lighter particles deflect more, heavier particles deflect less. And with this, you get now a scale, or you can have a bin, like a bunch of sacks where you collect those things, and with this, you have the position, which sack it is, the position gives you the mass number, and the amount that's in the sack is determined by the height of the signal. If it's double as high than the other signal, then it's twice as many. If it's 3 times as high, it's 3 times as many, and so on and so on. So we did that, and then we combusted acetylene. Combustion is always reaction with oxygen. Combustion of a compound is the reaction with oxygen. So if you have a hydrocarbon, and these were all hydrocarbons, they contain carbon and hydrogen, and we combust those, what do we make? What do we make? Water and carbon dioxide. And this, of course, depends how much carbons you have in your hydrocarbon. If you have 1 carbon, you only can make 1 carbon dioxide. If you have 2 carbons, you could be making 2 carbon dioxides, and so on and so forth. That would be here. You could make 2 carbon dioxide. But you could make 3 carbon dioxide. How many waters could I make with this? 6 waters. So the hydrogen is converted to water, H2O. 2 hydrogen, 1 oxygen gives you water. Now you measure the ratio of hydrogen to oxygen. Actually, you measure it by measuring the ratio of CO2 to water. And you get an intensity ratio. You know, the combustion of hydrocarbon can only go to CO2 and water. So CO2 is mass 44, and water was mass 18, or still is mass 18. So you have a signal at mass 18 and a signal at mass 44. And the ratio of these will determine how many carbons and how many hydrogens you had initially in your compound. And this will give you an empirical formula. That ratio will give you an empirical formula insofar that the molecule itself might have a multiple of this ratio. So the empirical formula, for example, for methane, would carbon to hydrogen 1 to 4. For ethylene, carbon to hydrogen 1 to 2. And for acetylene, carbon to hydrogen 1 to 1. This is the empirical formula. And this is what you get from the mass spectrum. You don't know how many multiples of those you have in a real molecule. So what you do before you combust it, you run this through a mass spectrometer and see how many carbons and hydrogens you have there, and then you combust it, and then compare it, and then you get what we call the molecular formula. So these are whole multiples of the empirical ratio, and the empirical ratio is a whole number ratio of carbon and hydrogen in this case. So methane, what would be the molecular formula? Methane, CH4, that's the same. Empirical molecular ratio is the same. Ethylene, you would have 2 of these units. It's C2H4. That would be the molecular formula. And acetylene is C2H2. That would be the molecular formula. The empirical ratio is this here, and this is the true molecular formula. So let me ask you a question. We have 30 grams of phosphorus, and they react with 40 grams of oxygen to form an oxide. If you react something with oxygen, it makes an oxide, okay? H2O, for example, is an oxide of hydrogen. You can say it's hydrogen oxide. And so you make an oxide, and 30 grams react exactly with 40 grams. So I give you a molar mass, and that's about 30 grams per mole, it's 31 grams per mole, and oxygen is the molar mass 16 grams per mole. So what is the empirical formula of that oxide? Is it PO2, P2O5, or P3O4? Now you need to learn how to estimate things. 30 and 31 in these calculations are about the same, okay? I would say it's a mole. Why don't you think about this and give me your answer? But be quiet and think for yourself, please. The homework is due next week. Homework 1 is due next week, okay? And iClicker starts officially coming Wednesday. This next time iClicker starts. Then we count. And these are participation points. You can't give any wrong answers. Of course, there might be wrong the answer, but you still will be participating, and this is what I want you to do. I want you to have the right answer, but I will not deduce any points if it's not the right answer. You're here to learn, and to learn with each other, and not to fall asleep. That's why we have these discussions, okay? All right, make sure that everybody clicks in. That's important. Every time I ask a question or repeat the question, you need to be registered. And you need to have gone to iClicker.com to register your iClicker. That way I know who you are. There's a little number on the back. That's your ID number of the iClicker, and then it asks you for your student ID and your name probably. I never registered an iClicker, so I don't know. But you will know. Okay, let's see. See, one's snuck in here. It's not quite clear, but I'm very happy that you didn't say P3O4 because the ratio was 30 to 40. That's already a good start. So you have how many moles of phosphorus you have in 30 grams? About 1. And how many moles of oxygen you have in 60 grams? Don't say it, okay? So that's your ratio. Why don't you discuss it with each other? Come on, discuss it with each other. If you don't know each other, introduce yourself and talk to each other. Come out with the right answer. Don't forget to click in. Come on, click in. There's some missing. You need to click in. Okay? The safest thing is when I open it, you click in and then you change your answer to the right answer. Okay? That way you are registered. I want to make sure that you get credit for participating. This is close to 5% of your grade, actually. I'm so generous. Okay? All right, so 66 and 33. That's interesting. And we still have two guys who are extremely funny. Okay? Oh. And so now, I actually gave you the answer. 30 grams is about 1 mole, is that right? And these ratios are molar ratios. So how many moles is 40 grams of oxygen? 40 divided by 16, what's that about? 2.5. So the ratio is 1 mole of phosphorus to 2.5 moles of oxygen. But we need whole number ratios. So what do? Multiply it by 2. With this, it gives 2 to 5. Okay, there it is. Oh, you see, we're burning this actually, and there's this oxide that forms here, and I will show you an experiment about this. So it's 30 mass to 40 mass, and I gave you these data here. The mole ratio is 1 mole, and 2.5 moles is 1 to 2.5. We multiply it with 2 is 2 to 5. This is the imperial ratio. I know, and you don't have to know at this point, after I say it, you will know it, that the molecule itself is P4O10. So it's twice the 2 of those units, P4O10. That was very good. Now, let's do an experiment. Let's burn phosphorus in oxygen. We oxidize phosphorus with oxygen, and what we do usually, in order to get this a little better started, we use liquid oxygen. And liquid oxygen, that way, the phosphorus doesn't have to go in the room and find all these oxygen atoms. We give it in concentrated form, okay? Liquid oxygen. You can see a liquid oxygen. It's a beautiful blue liquid. Oxygen therapy. I feel strong. How about you? Careful, it's very cool. Yeah? You awake now? Okay. Liquid oxygen is blue, and during this class, not today, but in the course of this class, you will learn why it is blue. Very difficult phenomenon. Not easy to explain. So it has this beautiful blue color. And now we have here a jar. There's a Calbare on the jar. And now we're going to put some liquid oxygen in there and see if it becomes gaseous. It's in there. And Karen will put a piece of phosphorus in there. White phosphorus, and now we need something to get the reaction started. A little rod which she makes hot a little bit, and that's what she does. And let's see what happens. There's not going to be any noise, not much noise. Yeah. No. Okay, let's see what's happening. Karen warms up that rod to get the reaction started. Activation energy. Okay, so otherwise it would take off right away, but it's not. So we need to get a couple of molecules started. Obviously, it's an exothermic reaction. You will see how exothermic it is. Okay. Can you see yourself here? That's why they didn't have so good cameras, so good optics. That's how they could have made light in the movies. Later they had arcs, of course. And you see yourself, that's about, I would say that's at least 500 watts, at least. I can see all clearly. I can see it clearly now, okay? You know that song? Wow, that's 50 years old nearly. So here it is. I think Karen deserves a hand. Thank you. And Alicia at the booth also. She does a very good job. Okay, so now we have talked about matter, and I would like to talk a little bit more about matter and the interaction of light. You've seen light here, the interaction of light with matter. As we look at light, where does the light come from? From the light bulb? No. Where does it come from? From the sun, okay? And this is electromagnetic radiation. Light is electromagnetic radiation. What we see as light is electromagnetic. But there's a whole lot of electromagnetic radiation coming at us, which we don't see. Most of it we don't see, because our eyes are only sensitive to a very small region of the electromagnetic spectrum. So light essentially travels in the form of waves. And I want to show you today that it is indeed a wave. Then you will understand the wave nature of light. So it has an electric component and a magnetic component, and it travels along. Now, where do you see waves really well represented? We live in San Francisco, we live by the ocean, so you're at the water, exactly. You stand at the water, and there comes the wave at you. These long wavelengths, waves at the surface light, with a high crest, and a very long and deep trough, okay? And they go to the crest and the trough, and then they fall in, and then that wave goes up again and has another crest and a trough. But, so the distance between crest and trough we call wavelengths, all right? So now we have these tiny little choppy waves coming in there, okay? So they have a very small distance between each crest and trough. So they have a very short wavelengths. That means the choppy waves, if they would go by your head or by your eyes, the long wavelengths wave, they don't come often by. They just have a low frequency. So long wavelengths has a low frequency. Now these choppy waves, they have a very short wavelength that has a very high frequency. They come by all the time, one after the other, okay? And so this is how you have to look at electromagnetic radiation, how you look at waves as such. And I just explained it to you with the example of water waves. So you'll see here, but water waves travel with a much slower speed than light. Light travels with the speed, as the name says, of light. This is 300 million meters per second. 300 million meters per second, okay? That's a lot. But not very fast, actually, because it takes a long time for the light to get to us from the sun. So you have the difference between the crest here, the maxima, is the wavelengths, and this is the troughs, it's also the wavelengths. And then you have the frequency. The frequency is how often they come. And this is related through the speed of light. The product of the wavelengths times the frequency gives you the speed of light. If I give you the wavelengths, can you calculate the frequency? Yes, because you know what the speed of light is. It's c divided by nu. So that means they are inversely proportional to each other. Inversely proportional means the longer the wavelengths, the less the frequency. Or the smaller the wavelengths, the higher the frequency. Okay? So our eyes are not very good, actually. I'm happy that I have them, but they're not very good. We see only a very small spectrum of that whole, the small area of that whole electromagnetic spectrum that comes to us from the light. We see about from 400 nanometers, which is blue, to 700 nanometers is red. You see, I give that in nanometers. This is 10 to the minus 9 meters. So this is what wavelengths are. So 400 nanometers is a shorter wavelength, higher frequency, and 700 nanometers is a longer wavelength, lower frequency. So this is a longer wave. So there would be the infrared, if you have even longer ones, and if you have shorter ones, you have ultravisible, UV light. Okay. So actually, this is the electromagnetic spectrum. We see just this part of the electromagnetic spectrum. That's the visible light, which I just showed you these colors here in between there. So there's you have low frequency and long wavelengths. So you have infrared light. That we get this from the sun. We like it, you know. When the sun is warm, that's what it does. And microwaves, you don't want to sit in there. Of course, somebody once put his dog in there to dry them. This is actually cruel. I've never tried it. The dog can survive this. And you have radio waves. And then you feel the ultraviolet part of the sunlight by getting sunburn. So you feel the effect, the interaction of radiation with matter. UV light saps you, and it also can cause, if you get too much of it, skin damage, permanent skin damage. Then you have X-rays. Many of you got an X-rays. This is even higher frequency. Then you have gamma rays, and there are some rays coming from the cosmos. They're hitting us. These are cosmic rays. They have very high frequency. Scientifically, it looks like this. Okay. So this is, again, these are wavelengths increase here up to 10 to the 8 meters. And MRI waves, NMR, radio waves are very long wavelengths. Then you have microwaves, they get shorter. Infrared gets even shorter. There's our visible range, okay? You got 10 to minus 9 meters something. And UV and X-rays and gamma rays and so on, they have very short wavelengths, but very high frequency, okay? Directly, inversely proportional to each other. So we see this part of the light. And if I look at this light here, I don't have the daylight, it looks sort of white. And because it's the mixture of all these wavelengths here that appears to us white. It's called polychromatic light. Light of many wavelengths. Polychromatic light, okay? Now, of course, you have possibilities to take that light and split it into its individual wavelengths. You do this with a grating. You have a CD seen in the light. What do you see? Colors, don't you see? You see exactly these kind of, you see exactly these kind of colors. So what the CD does, these little grooves, it diffracts the light as it shines off and puts it in different directions depending on their wavelengths. That's what you see. So I gave you these glasses today, the clear glasses. If you can take those out, please. The clear ones, not the colored ones. You need the clear glasses. Nobody has clear glasses? I have some clear glasses here. They forgot you in the front here? Oh, that's terrible. You get colored later. Or from your neighbor. Yeah? I don't have any. You must have come later. Okay, so now, so you look carefully at these glasses. Take them off and look at them. You see anything in there? There's some tiny, tiny little grooves in there, circular grooves. Okay? Just like in a CD has these grooves, but they're much smaller. Now look into this light here. You see the individual wavelengths? You see all the colors that I showed you? The rainbow effect, that's what it is actually. When you see a rainbow, you have these raindrops in the air, and they diffract the light into different wavelengths. They take it and separate that monochromatic sunlight into the different wavelengths of the spectrum. Okay, everybody seen it? Even the ones without glasses? Take some glasses from somebody else. Okay, so now we know that light. More? I aim to please, okay? All right, I gotta get on. So we've seen that polychromatic light can be split into individual wavelengths of monochromatic light. Light of one wavelength, monochromatic light. So I have, for example, here, that laser has monochromatic light. It's 532.2 nanometers. That's green. And if you have a red laser, you have 612 nanometers. It's red. So we are able now to make monochromatic light. Very cheap, actually. Didn't used to be like this. And so now what I want to convince you of is to make an experiment. We do it in our thought, but I put it also on BSpace. It says Dr. Quantum, double slit. Okay? Go there and have a look at this. Also, this lecture and the next lecture we're going to talk about. So let's assume we have a hole, a small hole in a surface, small hole, okay? And you have a light behind here, a polychromatic light. You shine a polychromatic light on the wall. You all did this, or some of you did this, of course, not all of you. You have a pipe light, put a tiny little pinhole in there. You take a flashlight behind it, and you hold it against the wall. And the wall, you see this concentric, very bright spot in the middle, and that gets diffused to the outside. And so that was essentially a slit. You have a slit there, okay? So I don't know why everybody did that, but people did that, okay? And so what you get a very intense, very bright spot in the middle. And as you go to the outside, it becomes dimmer and dimmer. It diffuses. And this is how we can, this would be the wall here, and this is how we can signify this. This is the distribution of the light. So that's very bright here, and that's dark here. And in between it's diffusing, gets dimmer. That's what you get with polychromatic light. Now let's make a second slit on there. Well, let's take that slit, let's do the same thing, we get the same thing. Now let's have two slits. What would you get? Two of those in the red. You get two of, yeah, there it is, okay. There's a bright spot here, and then it gets dimmer as you go to the outside, gets dimmer as you go to the outside, bright spot here, so you see two bright spots that sort of diffuse into blackness. Now, let's assume that we put laser light behind there, a monochromatic light of one wavelength only. This is what you get.